Hello students, this is Dr. Diaz again, and let's keep it talk about gas. In the previous class, we talked about how the variables like pressure, volume, and temperature, a number of molecules affect the gas behavior. And we talked about the gas laws as the Charlie, Gay-Lussac, Boyle's law, and combining gas law. Now, in this chapter, we're going to talk about pressure, vapor. We're going to talk about the ideal gas law, and will be all about the gas. So I would like to start with the vapor pressure and explain what is that. So the vapor pressure, in the very common words, is when the quantity of molecules in a container, we are talking about closed system over here, right? Because I don't want to see the gas going away. So vaporize is the same quantity of the molecules that will condensate. So the vapor pressure, of course, will increase when the temperature increases because we're gonna have more molecules. Let me grab my pen over here because that always helps me to explain better. So you see here the molecules are evaporating, so the liquid ethanol over here is evaporating. But at the moment, the molecules heat the wall of the container. The wall is colder, so the molecule will start condensate, right? So we'll have the number of molecules that are condensating equal the number of the molecules vaporizing. And here in Florida, mainly because it's a very hot place and full of water, because of course it's a peninsula, we have water all the place around us in the lakes as well. So we feel when it's getting hotter, like high temperature, we feel the humidity or moisture is increasing. We can even feel that we sweat more, right? We feel like I'm sweating all day because it's high moisture in the air. So, and of course, we don't only have one gas. Sometimes we have a container, or even in your room, you have your room. So the gas that you have around you, it's oxygen, CO2, SO2, a lot of different gas. So how the pressure works over here, so the total pressure will be equal the sum of all the partial pressure of each gas. So if I have like a container over here with gas A, I will call gas A, the blue one. So the gas, exert pressure because they are always in movement, so hit the wall of the container, so that is exerting pressure. Remember, the pressure is the force over an area, right? So, but sometimes I have more gas. Imagine if I have another gas, I will call gas B. So this gas will also exert some pressure. So the total pressure over here would be the pressure of the A plus the pressure of B. And this is what the Dalton law of partial pressure states, that the total pressure of gas mixture is equal the sum of the individual pressure for each gas in that experiment or that room or the container that we're studying. So the pressure exerted by each gas we call partial pressure. Okay? So I can give you a very simple example over here, and then you ask yourself like, oh, of course she's gonna give you a very simple example, and then the test will be hard. No, actually it's pretty easy if you understand the concept. It's easy to know, like, okay, I have a lot of things over here. It's like a weight. If you have two persons over here, so I will not exert the pressure by myself. I have one more person, so the pressure will be exerted by two, right? It's the same thing with the gas. So you have a lot of gas, we need to sum all the gas because the pressure will be exerted by each gas. So in this example, we have a sample of a noble gas. So we have a helium, neon, argon, and krypton over here. If the partial pressure of helium is 125 milliamps mercury, I have a neon 45, I have argon 158, and I have a krypton 17. The only thing you need to do to prove the Dalton law is use the formula. So you know the total pressure will be the sum of all gas. Just remember, pay attention on the units because sometimes I can mix the units, give you atm, millimeters mercury, so we need to convert, okay? And also, we can collect gas over water. Sometimes we need to estimate the volume that we produce in some reaction. Imagine if I'm producing ethanol, and the only way to find out how much I'm producing is also by, it's not the only way, but it's also by collecting the CO2 to produce it. How are we going to do this? Is we can measure the volume of gas by displacement. Remember how we measure the volume of something with like a weird volume, like a structure? We go and put the piece inside of liquid, so the water displaced will be the volume of that piece, right? Will be the same thing with the gas, but now it's the gas that will displace the water. So the gas collected is referred as wet gas, like in this example over here. So the amount of the gas produced, see that we have reactions here, sulfuric acid over here, and then the bubbles are going up, so that is hydrogen. So, and then we call a wet gas, since it also contains water vapor over here. This water vapor is actually the vapor pressure of water. Okay, vapor pressure of water. So, oh, my table is a mess now over here, but don't worry. I will go to another example and you're going to see the table. So the table is going to show you the temperature and also the pressure for that temperature. So remember, when you increase the temperature, we increase the vapor pressure. So if you apply the laws of Dalton law of partial pressure, we can determine the pressure of the collected hydrogen gas. So the first thing that we're going to see in a problem like this, for example, the atmospheric pressure. So the atmospheric pressure here is the total pressure, okay? So it's 755 millimeters mercury. So the water temperature, it gives us the temperature of water, so it's 20 degrees Celsius. When you give it this, it's because you need to go to the table of the vapor pressure to look for the pressure. What is the pressure exerted by the hydrogen gas? So the total pressure will be the sum of the pressure of the hydrogen plus the pressure of water vapor. And in that table, there was a mess up before. So you see that we have the temperatures over here. See that is increasing. Look at the pressure. So for 5 Celsius degrees, I have 6.5 millimeters mercury. If you go to 50, look at the pressure. It's already 92.5 millimeters mercury. Okay, that is the vapor pressure for water. So that is the data I needed. I had 20 degrees Celsius, so this is the data I needed. 17.5 millimeters mercury. Okay, so this is what I'm going to do. So we have a Dalton law. We know, I will not give you the Dalton law. You need to know that the total pressure will be the sum of both gas inside. So I will isolate this, so will be pressure of hydrogen be atmospheric pressure minus vapor pressure of water. So again, I'm bringing here the table. So we have the 17.5 millimeters mercury. So now I'm going to put the atmospheric pressure that was given by the problem, 755 millimeters mercury, minus 17.5. Now I have the pressure of a hydrogen over here. Good? Pretty easy, but you need to know the concepts. Now that I'm solving with you, it's like, oh, it's really easy. But you need to read and understand, like, okay, it's not only hydrogen being produced over here, so we have vapor water. So in giving the temperature, I can have the table and looking for the pressure and calculate easily. Okay? So kinetic, remember, kinetic is all about movement of the particles. So kinetic molecular theory of gas. Gas, again, I already talked about this before, but gas are made up of tiny molecules. They demonstrate rapid motion. Of course, they are always in movement and straight lines and travel in random directions. That means can go in this way, or can go in that way, or can go in that way, or can go in that way. Doesn't matter. Gas molecules have no attraction for one another, so they will not interact forming new substance. Gas molecules collide without losing energy. The average kinetic energy of gas molecules is proportional to Kelvin.